And we'll just talk about different kinds of sorts here. I've heard of some of these years ago. Some of them I didn't know about before reading this chapter, but it is a super important topic. You very often have to sort a list. As we talked about before, a lot of the procedures to find things in a list require that list to be sorted. So the bubble sort is the one I've heard about at least 50 years ago, where you compare neighboring items in a list and just flip them if necessary. So here you compare 45 to 23, and you're trying to put the big ones on the right, so you flip them. Then you compare the next two, 48 to 57, and you don't flip them. And the point is, after one pass through the whole list, the largest element has been found and moved to the right. Whenever you get to the largest element, it will, of course, fail all these comparisons and get moved. So this is why they call it the bubble sort. It's like bubbles rising in a glass of fluid. One bubble is trying to get to the top, and it goes gradually to the top. Then another bubble goes gradually to the top, and so on. So it will, of course, sort a list. Its problem is not very effective, of course. You have to do n-1 operations for the first one, n-1 comparisons to move the first one to the top in the worst case, and then n-2 and n-3 and so on. And this is a very famous sum. Gauss found the solution for this long ago, and it was known before that. If you want to add this series, the easy way to do it is make 2 copies of the series and put the second copy in the other order. And now if you just add this is n, and this is n, and this is n. So there are n terms, n-1 terms, and they're all the same, n, so the total number is n times n-1 over 2. So that's order n squared, of course, and that's why the bubble sort is not very efficient. That's complexity of n squared. Therefore, for a large list, it will get prohibitively slow pretty fast as your list gets larger. So that's why these other ones exist and are worth talking about, because they're better. So then there's the insertion sort. So you have you make a sublist, and the sublist is sorted. When the sublist only contains one element, it's clearly sorted. You don't need to sort one element. Now you make the sublist one bigger, and now you insert this into the right position of the sublist. And I guess they're trying to, so you take the 23 and you put it to the left of the 45. I think this picture should be the other way. And then you take the next one, which is 87, and put it in a correct place in the sublist. So this region that is sorted just grows and grows as you put these items in the right place one by one, and eventually that's the whole thing. That's the insertion sort. The first insertion takes one comparison. The next one could take 2. You could have to, when you put this 87 in there, you have to see, is 87 bigger than 45? Yes. Here, is 87 bigger than 23? You have to do both of those comparisons before deciding where to do it. So again, the next one takes 2, next one takes 3. So you have a total from 1 up to n-1. So in fact, it's the same as the bubble sort. That's complexity n squared. All right. One advantage of this one is it's somewhat useful if the data comes in one by one. You just insert it into the list. So that's one case in which this might be the right choice. And then there's selection sort, where you move the smallest element to position 1, the next smallest to position 2, etc. So it's pretty much the reverse of the bubble sort. And that's the game. You just fill in the lowest element to the top. All right. And let me check for comments in the Twitch. There. Feels very high school level drum. Probably Trump and such. Yeah, you're the greatest. Yeah, okay, good. I'm glad you guys are happy. Yeah, I like the conversing about current events is important, especially in the world of security. There's so much exciting current news. Anyway, all right, so the selection sort, the first element, and here the point of this was, we have to find the smallest element to put it at the front. So finding the smallest element might take n-1 comparisons to search through the whole list, and the next one might take n-2 and so on. So once again, we got pretty much the same thing. Order n squared. So now we finally get the stuff that works better, like quick sort. And the thing that's missing from all the previous ones is you never split the list in half. So you never benefited from any kind of like logarithmic improvement. Now we're going to do that. We're going to choose a pivot element, and now we're going to partition the list around the element, placing the smaller elements on the left and larger elements on the right to make 2 sublists. And then we're going to split the sublist. And the point is, after you do the first operation, some large portion of the list, like half of it, is now no longer worth worrying about. You don't have to compare it again. So some part of it is going to have a logarithmic comparison. So use 45. So you take all the elements to the left, less than 45, and put them here, and all the ones greater, and put them there without sorting them. But now you have 2 sublists, and you know that all the ones over here are bigger than 45, and all the ones over here are lower than 45. So half of these you never need to look at again. And that's where you're going to get a logarithmic improvement. So we're looking, here's the 2 sublists. And so partition takes order of n times. You're going to have to compare the pivot point with every element to decide which side they're on, and you have to repeat that log n times, so it's going to be n log n on the average. Now in the worst case, if you choose for partition the largest element by bad luck, then you don't actually split the list in half or anything like it. You just have that, and then you have to go through the whole list again. So in the worst case, it's as bad as the bubble sort, n squared. But for most cases, if you have an average amount of luck picking an element that's more or less near the middle, then it'll be n log n instead of n squared, which is a large improvement. All right, and Tim sort is what Python uses. This is the default, so it's a general case valuable. What you do is you divide the list into blocks of a fixed size like 32 or 64, then you use insertion sort on each block, and then you merge the blocks with merge sort. So this is Tim sort. You break it into runs, 1 and 2, and then you use insertion sort to sort those sublists, and then you merge them together. That's what Tim sort does. And you can see the code that does it, which is pretty obvious. This is an insertion sort. So you go through it, and you have your insort value is the unsorted list. And so while the unsorted list is greater than the insertion value, then you move forward until you find a place to put it. Insert it in the already sorted list where it belongs. You keep going until you find an element that's greater than it, and then put it to the left of that element. And here's the merge sort. They have two sublists, and so you have a merged list. You just go here, it's the length of the, as long as there's elements in both lists, you just check to see if the element in the first is less than the element in the second, in which case you merge it. And since they're sorted, you know the first element is the smallest element in the second list, and the first element is the smallest element in the first list. So you only have to compare the first element to decide which one to put in, and then just do it over and over. So here's the combination of them. You see, in the worst case, Tim sort is n log n. Quick sort is similar. And in the best case, the best you get is order of n for Tim sort, if you're lucky. And so that's a summary of it all. Whereas these guys tend to have n squared, these simple ones. Bubble and insertion and selection tend to be n squared all the time, which is pretty bad. N is what you can reasonably get to. Only if you're very lucky will this be order of n, which means every time you guess an element, it's the perfect element. Yeah?
So for like these kind of sorts, obviously it says worst case. What like would be kind of a simple example of how you get to like a worst case? Is it just like you have like
for which one? Any of them?
Any of these?
Oh, it's easy. The worst case, for example, for the bubble sort, is that the list is completely sorted backwards. So the first element is the biggest one, and you have to hop it all the maximum number of hops. And the next element is the biggest one left. You have to hop almost n minus 1. That's the worst case. Worst case is when it's the backwards. And for things like the quick sort, where you split it in half, the worst case is that every pivot point you choose is at an end. So you don't split the list in half. You just put one element on it, and you still have n minus 1 to hunt through.
So just like whatever causes the most work for this element.
Right, that's it. And so most likely to have the average case most of the time.
Yeah.
But good. All right. Let's try a Kahoot. I've got some ready. Let's see if there are any comments here. No new comments, okay. All right, this is chapter 11, so there's the Kahoots. Oh, let me make this fit on the screen a little better, especially for the people connecting over Twitch. Something like that should be right. Okay, the number is showing, that's what I want. If I don't do it right, this number is covered up on my face, but it looks like it's right. guess we got everybody that's coming. That's rude. Got it big again. All right, which one uses divide and conquer? Quick sort is the only one that keeps splitting the list in half. All the rest amount to pretty much the same as the bubble sort in practice. All right. That's why it's actually quicker, hence the name. All right. What's Python's default sorting? Sort, and you know, obviously they chose it because it's usually the best. All right, which one breaks the list into runs of 32 elements? Tim sort again. That's how it works. All right, good. All right, come on.